In this video lecture, we're going to discuss mixed strategy Nash equilibrium. So we're now on to chapter 11. I'll call them MNE for short. Yeah, the definition is simple enough. You have a strategy profile sigma equal to sigma 1 for player 1, sigma 2 for player 2, all the way out to sigma n for player m, is a mixed strategy Nash equilibrium if and only if the utility to player I of playing sigma I, given that everyone else is playing sigma minus I, so the profile in question, sigma, is a Nash equilibrium, if and only if the utility to player I of playing in that profile is greater than or equal to the utility player I could get playing any other pure strategy to everyone else playing in that same profile. And that has to be true for all possible pure strategies in player I strategy space, and this also has to be true for all players I. Okay, so unpack that a little bit more. So a particular mixed strategy, now remember what a mixed strategy is. Sigma 1, sigma 2, sigma 3, these are probability distributions on the strategy space for each of those players. So sigma 1 is the probability distribution on S1, all the pure strategies available to player 1. So that strategy profile, the strategy of mixed profiles, and remember, a mixed profile can also be a pure strategy profile, just not the reverse. So we're allowing for each of those sigma i's to be pure strategies if we like, but also mixtures of the pure strategies. Okay? So this strategy profile sigma is a mixed strategy Nash equilibrium if for each person in that profile, what they've adopted in the profile, their particular sigma I, the utility they get from it is greater than or equal to the utility they could get from anything else, given that everyone else is playing the profile. All right, so as long you can't take one player and say, if everyone stays the same and I move this one player, can this one player do better? In a mixed strategy Nash equilibrium, he cannot. Okay. Note that you only have to compare it to all of the alternative pure strategies that she has, and you don't have to compare it to any mixture of pure strategies. And this goes back to something we've talked about a lot of times, that if the mixed strategy gets me a utility of, say, 5, and it's better than what all the pure strategies get me, so there's pure strategies that get me other values, then mixing those other values isn't going to do any better. So putting a probability distribution on those other values from the pure strategies, I'm not going to be able to beat the number that I currently have. Okay, so I don't have to check for any mixtures of those pure strategies. If the mixed strategy is better, I can't beat the pures. Okay. Greater than or equal to. The equal to part is going to be important down the line, but we'll get to that. All right. So again, as with pure strategy Nash equilibria, we only have to consider rationalizable strategy. So a non-rationalizable strategy could never be part of a mixed strategy profile in equilibrium. Okay. And an important result, it's called well, doesn't matter what it's called for you guys. There always exists. Oops. A mixed strategy Nash equilibrium. Okay? And again, that includes pure strategies. So if you are looking at a game, say you're looking at a matrix game and there's a pure strategy, Well, Equilibrium. Well, of course, that is also a mixed strategy Nash Equilibrium. If you're looking at a game like Matching Pennies, so we talked about that one in the last chapter. Matching Pennies is a game where if they both come up heads or they both come up tails, I win. And if one comes up heads and one comes up tails, you win. Okay? Well, we get to put our pennies down on the table simultaneously. In Matching Pennies, the there is no pure strategy Nash Equilibrium. We looked at that in the last chapter. There is a mixed strategy Nash Equilibrium. It's where each of us plays heads or tails with probability 0.5. All right? So that's a mixed strategy Nash Equilibrium. So if I play heads half the time and tails half the time, and you know that I'm playing with that probability distribution, and your job is to try to pick the opposite of me, well, no matter what, you could pick heads every time, or you could pick tails every time, or you could pick any probability distribution that you like, and you're always going to come out winning half the time, right? So that's it. If I'm playing 50-50, it's not possible for you to win more or less than 50-50. Okay, no matter what you do. Which means that anything you do is a best response. Right? So if I'm playing 50-50, anything you do is a best response, including 50-50. If you're playing 50-50, anything I do is a best response, including 50-50. So if we're both playing 50-50, we are both best responding to what the other player has done, which makes it a Nash equilibrium. If I play anything other than 50-50, and your job is to do the opposite of me, like say I play heads 2/3 of the time and tails 1/3 of the time, then you should play tails all of the time, in which case you'll win 2/3 of the games. Which is the best response for you, but then in response to you playing tails all the times, I should play tails all the time, so playing heads 2/3 of the time was not part of a best response, so it can't be part of a mixed strategy equilibrium profile, right? And that's true for any probability distribution either one of us picks, except for 50-50, okay? So any probability distribution I pick other than 50-50, you can beat me, or you can win more than I do. Your best response is to pick the coin with opposite face of the one that I'm putting more weight on, because you're trying to pick the opposite of me, right? Which then that's a pure strategy for you, to which I have a pure strategy best response, right? So there is no there can't be part of an equilibrium profile for me to do anything other than 50-50. And this brings up an important point. In mixed strategy Nash equilibrium, what we're going to do is we're going to mix to keep the other person indifferent between changes. So I'm never going to be mixing between A and B, because A and B because there's like a sort of a perfect mixture of A and B that makes me the happiest. I'm going to be indifferent between A and B. And I'm going to mix to keep you from changing what you're doing in the profile, not to make me happier. I could care less if I play A or B, right? This goes back to the idea of a best response sets. We're only ever going to mix from best response sets, okay? So I have a best response to your strategy. If that best response is unique, if it's a pure strategy, that's what I'm going to do. I have no choice. Like, why would I do anything other than do the best I can? If I was a tie between stuff that I could play, like if A and B are tied, if they're both best responses to what you're doing, then I'm fine mixing, and I'm fine not mixing. I'm going to mix if by mixing I keep you from changing what you're doing. So mixed strategy Nash equilibrium is all about mixing from best responses to keep the other person from changing what they do. Another game that has a similar flavor to Matching Pennies, rock, paper, scissors. In that game, you have a very similar kind of flavor. Each of us plays rock, paper, and scissors 1/3 of the time. Right? So if I play rock, you should, if I play rock all the time, you're going to play paper all the time and beat me. But if you play paper, I'm going to play scissors. And if I play scissors, you're going to play rock. So there's no pure strategy Nash equilibrium. And there's any other mixture can be exploited other than 1/3, 1/3, 1/3. So if I play rock half the time and paper half the time, that means that, let's see, if I play rock half and paper half, but I never play scissors, if I never play scissors, then you're never going to play rock, right? And if you never play rock, why would I play rock and paper only? Because paper, the only thing it's good for is beating rock, and so it destabilizes that profile, right? So there is no profile except for 1/3, 1/3, 1/3. Now, not all Nash equilibria have equal probability on all the strategy space, all right? These are just kind of special cases, but they're kind of illustrative of the way that mixed strategy Nash equilibrium work. I don't play, if you're playing rock, paper, scissors 1/3 of the time each, it doesn't matter what I do. I could play rock all the time if I like. I'm going to win 1/3, tie 1/3, and lose 1/3. That's just the way it is. So whether I play a pure strategy or any mixed strategy, I'm going to get the same thing. You're playing one, but if I do anything other than 1/3, 1/3, 1/3, it incentivizes you to change what you're doing. So you're no longer going to play 1/3, 1/3, 1/3. And that's the essence of mixed strategy Nash equilibrium. Okay? So let's look at some games, really. That's all we're going to do in this chapter, is just look at a bunch of examples, because this is the only definition for the chapter. So here's a lobbying game. Player 1 can lobby or not lobby. Player 2 can lobby or not lobby. The payoffs are -5, -5, 10, 10. But they're asymmetric on the off diagonals. Player 1 gets a little bit more juice by lobbying when the other player does not lobby. All right? So if both players don't lobby, they do relatively well. If they both lobby, it costs a lot of money, but it doesn't do them any good because they're both lobbying. But if one lobbies and the other doesn't, he's able to exploit that advantage and get something passed, right? So these are competitors that are lobbying Congress, say. Okay? We have two pure strategy Nash equilibria in this game. So if I'm going to lobby as player 1, your best response is to not lobby, and if you don't lobby, my best response is to lobby. So these are pure strategy Nash equilibria. But there's also going to be a mixed strategy Nash equilibria in between those two. Okay? So if we put probability P, 1 minus P, Q, and 1 minus Q on those strategy spaces, I contend that there's also a mixture. I could play L and N as player 1 with a mixture P, 1 minus P, and you could do the same with Q, 1 minus Q, and there exists a mixture where, given that mixture, neither one of us has an incentive to change our own individual mixture. So there's going to be a mixed strategy in between the two. Okay? So how do I go about finding that? Well, to keep player 1 indifferent. Now, again, this is the key. We'll write it down. Okay, so the key is to keep the other player indifferent using your own mixture. To keep player 1 indifferent, player 2 has to adopt a Q that makes L and N for player 1 give the same expected utility, right? So if we have, for player 1, if player 2 is going to play Q, the utility of playing L is -5 times Q plus 0 times 1 minus Q. Oops, sorry about that. We're trying to keep player one indifferent, right? So we got to go down the we have to look at player one's playoff, not player two's playoff. So to keep player one, here, let's write this down. To keep player one indifferent, we need that -5, her payoff of playing L when player 2 plays L, times the probability of reaching that, which is Q, plus 25 times 1 minus Q. We need that to equal the utility of player 1 playing N, which is 0 times Q plus 10 times 1 minus Q. Okay, so again, this is the utility of player 1 playing L, given the mixed strategy profile Q1 minus Q. I'm just going to leave that as a blank space for space concerns. And this is the utility to player 1 of playing N, given what the other player is doing in the equilibrium. Okay, so we need the utility of those two pure strategies to be equal to each other. If they're not equal to each other, player 1 is not going to mix between them. All right, so in order for player 1 to mix between L and N, she has to have the same utility from L and N, and to have the same utility, if the other player is mixing, we need to use the expected utility. Okay, so we have negative Q plus 25 minus 25Q equals 10 minus 10Q, and thus, oops, sorry, I missed my 5 there somehow. Okay, so we have a 25 minus 30Q on this side is equal to 10 minus 10Q. And so we're going to have 15 on this side and a 20Q on that side. And so Q equals 3/4. Okay? So in order for player 1 to be willing to mix between L and N, we need Q equal to 3/4, and thus sigma 2 equal to 3/4, comma 1/4. And now, to keep player 2 indifferent, we're going to need -5 times P plus 15 times 1 minus P to equal 0 times P plus 10 times 1 minus P. Again, this is the utility to player 2 of playing L, given player 1's playing P1 minus P, probability distribution. And this is the utility to player 2 of playing N, given what the other player is doing. And now it's just a little bit of algebra. So the left-hand side is going to be 15 minus 15p minus another 5p. So we're going to have 15 minus 20p. And that's got to equal 10 minus 10p. And so we're going to get on the right-hand side 10p, the left-hand side 5. So 5 equals 10p, and so p equals a half. And so sigma 1 equals 1/2, 1/2. Okay? And that's, we'll put stars there to indicate that they're equilibrium profiles. So the equilibrium strategy profile, the Nash equilibrium profile that's not a pure strategy, that's only a mixed strategy, is sigma 1 equals 1/2, 1/2, and sigma 2 equals 3/4, 1/4. Okay? This is important on your quizzes, on your tests. When you're solving a problem like this, if you make it clear on your matrix what P and Q are, so in my matrix it's clear that P is the probability that player 1 plays L, Q is the probability that player 2 plays L. Okay? As long as that's clear, you don't have to write sigma 1 star and sigma 2 star for me. It's sufficient to solve for P and Q. So as long as I know that Q is the probability that player 2 plays L and 1 minus Q is the probability she plays N, if you solve Q equals 3/4, that's fine. Okay? But if I see Q equals 3/4 and I don't see what Q is, I can't give you full credit for it because I can't tell if that's supposed to be player 1 or player 2, if that's supposed to be N or L, etc. All right. So as long as your labeling is clear on the matrix, as long as it's obvious what Q and P stand for, if you write Q equals 3/4, P equals 1/2, that's 100% correct for a question like this. You don't actually have to write out the sigma 1, sigma 2. If you write out the sigma 1, sigma 2, that's totally fine. You know, that maybe makes my job a little bit easier, but the P's and Q's are fine as long as it's clear what P and Q means. Here we have another game called a tennis game. Okay, it's a 3x3. And I believe player 1 is the server in a tennis game, and player 2 is receiving the serve. Player 1 can hit a forehand serve, like a serve to the forehand side, a serve to the center, or a serve to the backhand side. And if player 1 serves to the same spot the player is ready for, it's a good thing for player. It's a good thing for player 2. Okay, but player 2's backhand's a little weaker, so even if she knows the backhand is coming and she's ready for it, she's still not great at it. Okay, and then if they hit the opposite, it's better for player 1. So if player 1 serves to the backhand and player 2 is ready for the forehand, player 1's definitely going to win that point, etc. Okay, and we'll just fill in some of the other, just to kind of help motivate where these payoffs come from. We could put a story on all of them as far as their relative strengths and weaknesses. Okay, now the first thing to think about is rationalizability. Okay. So, is there anything dominated for either player? All right. So let's think about player 1. If player 2 stands to the forehand, B is the best response for player 1. So clearly, B is not going to be dominated for player 1. If player 2 stands to the forehand, B is also the best. And if player 2 stands to the backhand, C is the best thing player 1 can do. So C is not going to be dominated. So the only possibility of domination for player 1 is a forehand. Okay? So, does there exist a mixture of C and B that dominate F? So neither C nor B dominates F, but is there a mixture of the two that dominates it? Okay, so that's the first thing I got to do. I got to try to find if it could, otherwise the mixed strategy profile on top of the 3x3 is going to be much more challenging to solve. So the first thing you want to do if you're looking for mixed strategy Nash Equilibria is use rationalizability to make the game as small as possible. That's not necessarily true with pure strategy Nash Equilibria. I showed you in the last chapter, it's actually quite easy to go through a big matrix and just do the double underline exercise. So ripping through the rationalizability is not necessarily the fastest way to find all the pure strategies. We just know that anything that wasn't rationalizable is not going to get a double underline in it, right? But for mixed strategies, really important. The first thing you want to do is definitely go through and use rationalizability. Otherwise, you're going to get yourself in trouble. It's a lot harder to go through. Okay, so let's see if there's a if F is dominated by a combination of C and B. All right. So if player 2 plays F, then clearly the combination of C and B is dominating F. Like the combination of 2 and 5 is going to dominate F. So column F is a check mark. Definitely works in column F. What about column C? So in column C, the mixed strategy for player 1, so we're going to go 0 times P plus 3 times 1 minus p, that has to be strictly greater than 2. Okay? So 3 minus 3p greater than 2, which means 3p has to be less than 1, p has to be less than a third. Okay? So we need p to be less than a third in order for c to be dominated. And then for column B, we need that, well, in this case, all we need is that p has to be greater than 0, which is true for any mixture. Because we have C, the payoff of playing C is 3, and the payoff of playing B is 2, and if she plays F, the payoff is 2. So as long as C gets any weight at all, we're good. So in column B, all we need is that P has to be greater than 0, which is going to be satisfied for any mixture. So does there exist a mixture that where P is greater than 0 and P less than a third? Well, sure. So as long as P is greater than 0 but less than a third, F is dominated. Okay? So F is relatively easily found to be dominated by a combination of B and C. F. So player 1 is never going to serve to the forehand. Okay? And now, clearly, F for player 2 is iteratively dominated. Okay? By C. So F for player 2 is now iteratively dominated, and we're left with the 2x2 game. Okay? So we're left by this 2x2 game, and there's nothing else dominated in here. Okay? If player 1 plays C, player 2 would like to play C. If player 2 plays C, player 1 would like to play B. If player 1 plays B, player 2 would like to play B. And if player 1 plays B, player 2 would like to... Sorry, if player 1 plays B, player 2 would like to play B, but if player 2 plays B, player 1 would like to play C, right? So there's no pure strategy Nash Equilibria in what's left over here. So there's no pure strategy Nash Equilibria in this game. No pure strategy Nash Equilibria, okay? But we know already that there's got to be a mixed strategy Nash Equilibria, so let's solve for it, okay? Now, to prevent confusion, the P that I used just now on C and B, that was a P to determine whether there was a mixed strategy of C and B that dominated F. So I wasn't solving for an equilibrium, I was just trying to get rid of something if possible, okay? So now, I'm still going to let these the strategy be P and 1 minus P, but now I'm looking at the mixed strategy, so I'm going to change the color. Okay, so just not to be confused by what the purpose of the red P's were versus what the purpose of the blue P's are. Okay, and for player 2, I'm going to use Q1 minus Q. I tend to use P1 minus P for player 1. Q1 minus Q for player 2, but not always, and it doesn't matter. You can use whatever letters you like as long as you label it. Always label it on your graph. Don't assume that I know what you're that I know what you're going to be using. Okay. All right. So to keep player 1 indifferent, we need for player 1 indifference, we need that. Let's see. 0 times Q plus 3 times 1 minus Q. That's going to be the utility of playing C. We need that to be equal to 3 times Q plus 2 times 1 minus Q, and that's going to be the utility to player 1 of playing B. And given the other player's mixed strategy profile. So that means 3 minus 3Q equals 3Q plus 2 minus 2Q. So we're going to have a positive 1Q, so I get a 4Q on this side, and then the other side is going to be a 1. So Q equals a fourth. Okay? And so that gives me sigma 2. In order to keep player 1 willing to mix in this profile, sigma 2 has to equal 0 for F, 1/4 for C, and 3/4 for B. That's sigma 2 star. Okay? And to keep player 2 indifferent, we are going to need that 5P plus 2 times 1 minus P, the expected utility of playing C, is equal to the expected utility of playing B, and so 2P plus 3 times 1 minus P. Alright, 2 plus 3P has to equal 3 minus P. So we're going to get 4P equals 1. Or P equals 1/4. Okay? And so also here, sigma 1 star is equal to 0, 1/4, 3/4. Okay? And there's an intuition here in that, like, it was clear that player 2 from the payoffs was not very good on the backhand, so player 1 is going to pick on it by serving often to the backhand. But if player 1 serves all the time to the weak spot, player 2 can set up for it and do reasonably well. So player 1's got to mix in sometimes to the center just to keep player 2 off her game a little bit. Okay? And that's the how to resolve this particular game. Okay? All right. So we move on to just examining a couple more games. Here's another 3x3. Up, center, down, left, middle, right. 8-1. There's no story behind this game, just some payoffs. Well, I mean, there's a story, I don't know it. There's always a story we can make up. Okay. Let's see. In this game, it's clear that for player 2, L is dominated by M. Right? So we can get rid of it. But there is no dominance remaining in the game. So neither M or R are dominated for player 2. It's obvious that U and C are not dominated. They are best responses to M and R respectively. But there's no mixture of U and C that's going to dominate D. You can verify that for yourself. But in order, yeah, the 3 and the 1 are not going to allow that to happen. Okay. You can get close, but it's not going to quite work. Now, this game also has pure strategy equilibria, so you can go ahead and identify those if you like. So if either with a double underline exercise, you're just kind of reasoning your way through. If player 1 plays U, player 2 plays R. If player 2 plays R, player 1 would play U. So UR is a pure strategy Nash equilibrium. And if player 1 plays C, player 2 plays M. If player 2 plays M, player 1 plays C. So that is a pure strategy Nash equilibrium. And if player 1 plays D, 2 plays R, and so that's it. So there's 2 pure strategy Nash equilibria, but there may also be mixed strategy Nash equilibria. So that's what we're going to do now is to try to identify mixed strategy Nash equilibria. Okay? So I'm going to look, I'm going to put probabilities here. Here I have P, 1 minus P. All right. And I'm going to put A, B, and 1 minus A minus B for the probability distribution of player 1. Okay, so notice that here, since there's 3 strategies and none of them are dominated, I'm going to assign a probability A to one, B to another, and 1 minus A minus B. Right? Or I could have used R as 1 minus R minus S, whatever you like. The important thing is that the third strategy is going to be a combination of the first two. Once you know two, you know the third one. Okay? And again, this is why you want to try to use rationalizability to the fullest extent possible before you try to find the mixed strategy equilibria. Otherwise, you're going to make yourself a mess. All right? You want to get rid of strategies to the fullest extent possible before you assign values to them in mixed strategy. Now, if we hadn't gotten rid of L by dominance, if I had just left it, put P, Q, 1 minus P minus Q up there, that would have been fine. I would have found that in any equilibrium, the probability on P has to equal 0. Right? If I had assigned P to the probability of L, we would have found that in any equilibrium, that P has to equal 0, but it creates a lot of extra algebra for me. So find rationalizable set first before you look for mixed strategy equilibria. Not important for pures, very important for mixtures. Okay? Okay, so for player 1 to be indifferent between U and C, requires that, let's see, if U and C are part of a mixed strategy. Now again, U, C, and D, any two of those or all three could be part of a mixed strategy. So there's a lot of things to consider, right? I'm like, well, I could think U and C could be part of an equilibrium, but if the values associate, I'll start these games as the following. I'll start with U and C because of the first two. Just the algorithm, just for me, works best that way. For you, you can decide how you're going to do it. But I look at U and C, and I ask, can U and C be indifferent? And if U and C can be indifferent to each other, there's going to exist a value of P that makes them tied, right? Now, if they're tied, I also have to next look at D. Because if under that probability distribution P, D is better than U or C, which are tied, then U and C can't be part of a Nash equilibrium together, right? I'll say it again. For U and C to be part of a mixed strategy Nash equilibrium, player 1 has to be indifferent between them. So we have to solve for a value of P that makes us indifferent. But if U and C, if we're indifferent to each other, if those two strategies are indifferent, if the player 1 is indifferent between strategies U and C, we also have to check D. And if under that probability P, D is better than U and C, which is entirely possible, like it would be entirely possible that if I find indifference between U and C that D is better, well then U and C just cannot be part of a mixed strategy Nash equilibrium, right? Because D is better under the probability that lets that happen. So then we would say, U and C are not part of a mixed strategy Nash equilibrium, but maybe U and D are, or C and D are, or both. Okay? So then I have to go and check those cases. Okay? So there's cases. I have U and C as a case, and I'm going to start off with that one. So if U and C, and then U and D is also a case, C and D is a case, and U, C, and D together are a case. So it's a whole bunch of cases, and I just got to try each and every one of those cases. So here, case 1, I'm going to look at U and C being indifferent. All right. U and C being indifferent, I would require that 0 times P plus 4 times 1 minus P is equal to 4 times 1 minus P, times P plus 0, okay? Which gives us 4 minus 4P, so it's going to be an 8P on this side and a 1 on that side. So P equals 1 over 8. Oops. Sorry about that. I got the only way this is going to be true is if P equals a half. Not sure what happened with my algebra there. I left the 1 instead of the 4. So we have 4 minus 4P equals 4P. And so 8 on 8P equals 4, or P equals 1 half. Okay? So indifference between U and C requires P equals 1 half. Okay? If P equals 1 half, so if P equals 1/2, the utility to player 1 of playing U, given that P equals 1/2, given, I guess since I already wrote it, I can put sigma 2, given that particular sigma 2, what is that expected utility? Well, it's 4 times 1/2, right? So it's just equal to 2. That's the expected utility. So what about if I play D? So remember, if the utility of D in that probability distribution, if the utility of D is bigger, if the utility D is greater than 2, then that destroys U and C being part of any mixed strategy Nash equilibrium. So we have to check. The utility of D, given sigma 2, is equal to 3 times 1/2 plus 1 times 1/2. And lo and behold, in this case, it's equal to 2. Okay? So in this case, when sigma 2 is 0, 1/2, 1/2, we have indifference for player 1 between all of those things. Okay? We have indifference for all. And when when sigma 2 is not 1/2, 1/2, right? Or 0, 1/2, 1/2, then D is never a best response. The only way D is a best response, because look, because if the probability on M goes above 1/2, then C is the best response, and if the probability goes below 1/2 on P, then U is the best response because of those 4s. The only way D is played is if P is equal to exactly 1/2, but when it is, player 1 is indifferent between all 3 of those strategies. Okay? So sigma 2 equals 0, 1/2, 1/2 must be part of any MNE excluding the pure strategies. Okay? Excluding the pures. All right, so we've proven that we have to have P equals to 1/2. It's the only way we're going to go mixed strategy. And when P is equal to 1/2, player 1 is willing to play all 3 of his. Okay? Now, we've got to think of what makes player 2 indifferent between M and R given player 1's mixed strategy. All right? Here, we're going to need that 2 times A plus 4 times B plus 3 times 1 minus A minus B. So I'll just write that as 3 minus 3A minus 3B has to equal 3A plus 0B plus 4 minus 4A minus 4B. Okay? So that's setting the utility of M equal to the utility of R. It looks like a mess, but it's not. It'll simplify for us. So we have 3 minus A plus B is equal to 4 minus A minus 4B. And so I can subtract 3 from both sides, so I get a 1 here, and I can get a 2, oh no, the A's fall out. Okay, a minus A on both sides, it falls out, and I have a 3B over here. Okay. Oops, sorry, there's not a 3B on this side, it's a 5B, right? So I gotta add 4B to both sides, so 5B. So B is equal to 1/5. So what we show here is that in any mixed strategy Nash equilibrium, we need B to equal exactly 1/5 in order to keep player 2 indifferent between M and R. Okay, and so sigma 1, which is equal to A, B, 1 minus A minus B, we now show that the middle spot is 1/5. that didn't affect the first position. That's still a variable, so that it can be flexible. So there's going to be a whole range of equilibria here. That's allowed to be A, and we can replace B in the last one. It was 1 minus A minus B, but we know B is 1/5, so it's going to be 4/5 minus A. Okay? So here, the mixed strategy Nash equilibrium, okay, for player 2 it's fixed. He's got to play 50-50 M and R. It's the only way you're going to have a mixture. But for player 1, the probability on C has to be exactly 1/5. That's the only way we're going to do that. But A could be 4/5, in which there's no weight at all on D. And A could be any value between 0 and 4/5, which is going to have a corresponding value on D. Okay? So with A less than or equal to 4/5. All right? So if A goes above 4/5, we're violating the laws of probability. We're going to have a negative probability on D. Okay? If A equals 0, that's allowed. Then we're just having a mixture of 1/5, 4/5 on CD. Okay? And A could go as high as 4/5, which would be a 4/5, 1/5 mixture between U and C. But we can have anywhere in between, where all of them are played. Okay? And notice here why that's important, that we're not allowed to get rid of D, even though... never mind. I won't go there. Okay? All right. So, yeah. Even though D is not a best response to anything player 2 can do, it can still be a very important part of a mixed strategy equilibrium profile. Right? There's a best D. Rephrase that. D is only a best response when player 2 plays P exactly to 1/2, but it's an important one because that is in fact the only thing that player 2 is going to do in a mixed strategy equilibrium. Okay, so anyway, so D is a best response, but it's only a best response to one very particular thing. But it turns out that very particular thing is part of an equilibrium profile. Okay, so that kind of makes this interesting. All right, so now we can move on to another game. This game is also a 3x3. U, C, D, L, M, R, X, 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 0, X, 0, 0, X, 2, 0, 0, 2, 0, X, 0, 2, 2, 0. Okay? We don't know what the value of X is. It's allowed to be anything, and we want to think about how the equilibrium of this game changes as X changes. All right? So the interesting things to note is that if player 1 plays U, he gets X for sure. That's his expected utility. And if player 2 plays L, she also gets X. That's her expected utility. So the pure strategy U and the pure strategy L return a sure payoff of X. Okay? And M and R return a mixed M and R for player 2, and C and D for player 1 return a mixed strategy payoff, and that mixed strategy payoff is going to be a mixture of 2 and 0, which makes it like a 2 times matching penny game on the inside, right? So if both players were only playing C, D, M, R, we're in a if neither player were playing U and L at all, that would be a matching pennies game with double the stakes. Okay, in a sense, right? So instead of it's just adding 1 to all the payoffs. So instead of 1 minus 1, minus 1 1, etc., you're just adding 1 to everyone's payoffs. Okay, yeah. So the loser is compensated by a penny, and the winner gets an extra penny or something like that. But it's a shift of the matching pennies game. The equilibrium will be the same, 50-50 on MRCD. Okay, so it's kind of like a matching pennies game embedded within another game with this variable X. Okay, now think about sort of what are the Nash equilibria here. Well, if X is less than 0, right? If x is less than 0, then u and L are dominated, right? So if that's a negative number, for example, M dominates L if x is negative, right? So U and L are dominated. So sigma 1 star equals sigma 2 star equals 0, 1 half, 1 half. Okay? That's the unique mixed strategy Nash equilibria. There's no pure strategy equilibria in the matching pennies game. They would just play 50-50 on CDMR. All right, so if x is negative, the game, the equilibria is very easy. Okay? Now, if x was greater than 2, then it would be clear that U and L are dominant strategies. So only that pure strategy U and L would exist. Okay? But we could also say, sort of, and so I'm not going to write that down because there's a richer set of things we can say about when x is greater than 0. But if x is greater than or equal to 0, UL is a Nash equilibrium. All right? So imagine x is equal to 1, and I'm player 1 and I play U, okay? Then if I'm playing U for sure, then player 2 would get 1 by playing L and 0 by playing M or R. So clearly she has a strict best response of playing L. And that's true for any x greater than 0. Even x equal to 0, if I play U as player 1, then the best you can do as player 2, you're going to get 0 whether you play M or R or L. So L is a best response, and the same for U. So it's a weird equilibrium. Like, I wouldn't expect people to play that one, but it is an equilibrium. Okay? So as long as x is greater than or equal to 0, then U and L are always in equilibrium. Okay? So it's not an equilibrium if x is less than 0. It is an equilibrium if x is greater than or equal to 0. All right, the next thing to see is that if x is greater than or equal to 0, and let's start thinking about mixed strategy Nash equilibria, I'm going to put p, q, and 1 minus p minus q. This time I'm going to put 1 minus p minus q on the first column. The reason is that M and R are kind of symmetric strategies in the sense that they both have the 2, 0, whereas L is kind of on an island by itself with these all x's. And so it's just a little bit easier to mathematically to put the A and B and the P and Q on the ones that are more similar to each other. Okay? Yeah. All right. So if x is greater than or equal to 0, the next thing to notice is that only mixed strategies have P equal to Q and A equal to B. Okay? Meaning the probability that player 2 plays M and R have to be the same. P has to equal Q. Okay? To see that, notice that if I'm player 2 and I'm playing M, my payoff is the payoffs are 0, 0, 2, right, on M, and for R it's 0, 2, 0. Those are the payoffs of M and R. If player 1 is not playing A or B equally, if he's putting more weight on A than he is on B, well, then the payoff of R is bigger than the payoff of M, so I'm not going to mix between M and R. I'm going to play R for sure. Okay? So the only way I'm going to mix between R and M is if A and B are the same. All right? Now, it's not to say that if A and B are the same, I am definitely going to mix between M and R, but it's a necessary condition. Okay? Let's say it one more time. If player 1 is playing A and B not equal to each other, if A is bigger than B, then R is a better thing to do than M, so I'm not going to mix between R and M. Okay? But if player 2 is playing R and not M, player 2 is not going to be mixing between C and D. She's going to want to play D. Okay? So the only way we're going to have mixtures up there is if P equals Q and A equals B. Okay? And that's an insight from this game. That's the most important insight from this game. Okay? Because that dramatically simplifies the math here. Okay? So now we can think of this as like, okay, this is P, and this is P, and then this is 1 minus 2P. Right? And then this is A, and this is A, and this is 1 minus 2A. It simplifies the problem. Okay? Now, for U to be part of a mixed strategy Nash equilibrium, we need U to be indifferent to C, right? So if U is going to be played, we need some indifference, because we know that C and D have to be indifferent to each other because of the result above. So if U is going to be part of it, it's also got to be indifferent, right? And for U and C to be indifferent, we need that 2 times P is equal to X, right? The payoff of C is going to be 2 times P. This is the utility player 1 of playing C. And then X will be the utility player 1 of playing U, right? That's always the utility 1 of playing U. Okay? So in order for U and C, if we're indifferent between them, we need that 2P is equal to X, which means that P equals X over 2. Okay? Now, this is not feasible if X is greater than 1. Okay? Because if X is greater than 1, then P is greater than a half, but there's 2 of them in there, and so that's going to force L to be a negative number. Okay? Not feasible if X is greater than 1. Okay? So we need X less than or equal to 1 for a mixed strategy, Nash equilibrium, for a pure mixture. Remember, the U and L is always in equilibrium. It turns out it's the only equilibrium if X is greater than 1. Okay? So in order to have a mixture of these strategies of U, C, D, L, M, R, we need X to be greater than 0 and less than 1. So there's a so in that game, like you first see X, and you're like, wow, it's like, how do I do this thing? It turns out there's only a very narrow range of X where the game has sort of, call it, interesting outcomes, right? If X is greater than 1, then we're only going to look at the pure strategy equilibrium, and if X is less than 1, we're only going to look at that mixture between the two right side and bottom strategies, MR, CD. Okay? So, if X is in the interval between 0 and 1, then we have that sigma 1 star equals sigma 2 star equals X over 2 for the 2 out, because P is equal to X over 2. And then this 1 minus 2 times P is just 1 minus X. And we get that from the above, because the P is equal to X over 2. Okay? And then, of course, we also always have the possibility of going to 1/2, 1/2. Okay? So, if X is greater than, if X is greater than 1, we only have the pure strategy profile. So we can kind of see if we have enough space over here. Only UL if X is in the interval between 0 and 1. So this is actually greater than or equal to. Oh no, if it's equal to what? No, sorry. If X is in the 0 to 1 interval, and we actually have a hard bracket on that side. We have the 2 down there, 2 below, right? These two. But notice that they're the same thing when X is equal to exactly 1. Okay? So this 1 minus X, X over 2, that is 0, 1 half, 1 half when X equals 1. Okay? So they collapse to the same thing. Okay? And then when X is less than, when X is equal to 0, that should have been only up there, X equals 0, we have the UL and the we have the UL and the 0, 1 half, 1 half, and when X is less than 0, we only have the 0, 1 half, 1 half. Okay? Just as a summary. So X is greater than 0, we have the pure strategy alone. X is between 0 and 1, we have both of the mixtures below, okay, along with the, we also have UL. We always have that one for X greater than 0 and 2 below. Right? So when X is between 0 and 1, we have UL and the 2 below. When X is equal to 0, we have UL and 1 half, 1 half. And when X is less than 0, we only have the 0, 1 half, 1 half. All right? So that's the solution to this game. And with that, we'll conclude mixed strategy Nash Equilibria.